Hello guys, welcome back to the second part of the video discussion for flexural stress. So I have here a second example. We have a flanged cross-section is used to support the loads as shown on the beam. So we have this beam here and the dimension of the shape are given. Consider the entire 6-meter length of the beam and determine the first one, the maximum tension bending stress at any location along the beam, and letter B, the maximum compression bending stress at any location along the beam. So I have here the 6-meter overhang beam. We have this load 3 kilonewton per meter. We have 3.2 kilonewton concentrated load and a 7.2 kilonewton concentrated load. And we have forces acting vertically, okay, that is at RB and RD. And this is the cross section of the beam. We have an I-beam wherein the flanged on the bottom is longer compared to the flanged now on the top. Okay, this is an example of an I-beam. This is the flange. This is the web. Okay. Now, we have already solved the shear and moment diagram of this one, and we will be using that shear and moment diagram to compute the flexural or the bending stresses in our beam. And for those who haven't watched the video discussion on the computation of the shear and moment diagram of this beam, so I have posted the link of that video discussion in the description below. And we have here, this one is the shear and moment diagram of this beam, and this moment here will be used to compute the maximum tension bending and the maximum compression bending stress. And we know that the formula for a flexural stress is equal to FB, that is equal to MC over I, where our M is the internal moment, the C is the distance from the neutral axis to the outside or the farthest distance from the neutral axis, and I here, that is the moment of inertia. Now for our I, for rectangular beam, we have already moment of inertia along the neutral axis, that is just BH cube over 12. Where our B here, that is the base, if these are rectangular, and H, that is the height. Now this is only applicable for rectangular that is symmetrical along the y-axis and x-axis. Now in this case, as we can see, we have symmetrical with respect to the y-axis, but it is non-symmetrical on its x-axis. Correct? So we need to compute the moment of inertia and use that moment inertia in this formula. So our dilemma here is to compute this moment inertia. Okay, and once we compute the centroid or the neutral axis of this beam, we can now compute for our C, that is from the distance from neutral axis to the point of tension stress or bending or compression or bending stress. So let's isolate this, or let's compute the I in this problem. Okay, so our goal here is to compute the inertia of this asymmetrical section. Okay, so that we could use the formula, that is the flexural stress equal to MC over I. So this should be computed, this I here. Okay, so we have this I-beam. Now this one is our flange and this one is our web. Okay, that's the part of our cross-section of an I-beam. So we need to apply the transfer moment of inertia formula, that is in terms of I, or the inertia at the neutral axis, is equal to the gross inertia plus AD squared, where A here, that is our area, okay, area of the one that we will be transferring in the neutral axis, and the D here, that is the distance from the neutral axis to the centroid of that area. Okay, so the first thing we do here is determine the location of our neutral axis. Okay, so let's assume that our neutral axis is it on this point, and that is, let's say that is barred Y, okay, from the bottom. And since we know that our section here is symmetrical along the y-axis, and let's say that at this point, this one is the origin, if we put our section in the Cartesian coordinate, that is y vertical and yx, so that's yx plane. So therefore, our centroid here is at, let's assume at this point, okay? So therefore, we could say that our barred x is equal to 0. Now, we only have y coordinates in our centroid. So let's say that's our barred y. Okay, so our goal here is to locate barred y, and that is also the position or the location of our neutral axis. Again, neutral axis is on the centroid of our section. So how are we going to compute for the neutral axis here? We can just use the Varignon's theorem, and that according to Varignon's theorem, that the summation of all the moment at any point of the force acting on a body is equal to the moment of the resultant at that particular point. Now, since we have a homogeneous section, so we have the same material, and that is, let's say, that is steel or concrete. So therefore, we could say that our area here, we are not dealing with mass here anymore. So we could say that the area total here times the barred y is equal to the summation of all the area. Okay, we can compute our area. So we can divide this section into several areas times the centroid of that area to our reference point. Okay? So our yi here is the centroid of that area, okay, from the reference line. So since our reference line is this one, that is our x-axis, okay, and we are referring the location of our NA here from the x-axis. So therefore, this is our reference line. So in that case, we need to compute the total area first. Okay, we have the total area that is equal to, okay, so let's divide the section into 3 areas. Let's say this is area 1, okay, this one is area 2, and this one is area 3. Okay, so we have first area 1, that is, we have 100, that's a rectangle, 100 times 20, plus area 2, that is 270, times the thickness of our web, that is 20, plus we have area 3, that is 20 times 210. This one. So therefore, we have our total area that is equal to 11,600. Take note, these are all in millimeter times millimeter. So therefore, we have the area that is in millimeter squared. Okay, so we can now use this equation, that is, we have area total, that is 11,600. Then we have unknown, that is the barred y, the location of our neutral axis from our reference line. Then we have is equal to our area 1 first, that is the summation of all the area times its centroid from the reference. That is, let's say we have 100 times 20, that's the area 1, times the centroid. Now let's say that's y1, the centroid of our area 1, that is equal to, we have, since the total length from the top surface to the bottom surface is 270 plus 20 plus 20, that gives us 310, correct? This one, that's 310. So therefore, our y1 here, that is equal to 310 minus half of 20, this is 10, correct? Since we have 20 millimeter thickness now in our flange, so therefore that's 10. So therefore, at 310 minus 10, this gives us 300 mm. So therefore, the centroid of our area 1, that is equal to 300. Then plus our area 2, that is the area of the web, that is, we have 270 times the thickness, that is 20 mm. So we have 20 mm. Now the centroid, now let's say that's y2. Now our y2 here, that's the centroid of our web, is equal to, now we know that this one is 270. Okay, so 270 divided by 2, that is equal to 135. So from this point, that's the centroid, up to this point, that is 135, correct? Then we add 20, the thickness of our flange, that is equal to 155. So we have our Y2 here, 155 mm. So we have 155. And lastly, we have area 3. Okay, that is plus the area 3 here, that is the area of the larger flange, that is 210. Okay, times the thickness, that is 20, times the centroid of area 3, that is at this point. So we have the distance, let's say that is our Y3. Now Y3, that is just the 1/2 of the thickness. So that is 20 divided by 2, that is 10. So we have here 10. And this gives us the value of our barred Y is equal to 127.5 millimeter. So therefore, the location of our neutral axis from the x coordinate, from the x-axis is equal to 127.5 millimeter. Okay? And our barred x, of course, it is equal to 0 if our reference or our origin is at this point. And now, since we have already computed the location of our neutral axis, then we can now transfer our moment of inertia of every sections to the neutral axis. Okay, so we can now compute the moment of inertia transform of the entire cross-section. And that we have the moment of inertia in the neutral axis is equal to gross moment of inertia plus the area of that section times the location or the distance of the centroid of that area to the neutral axis. And now let's start from section 1, this area here. So we need to use this formula, that is Ig plus AD squared. Let's say that is the transfer moment of inertia to the neutral axis from our section 1. That is equal to Ig, or the gross moment of inertia, since that is rectangle. So we have 1/12 base times height cube plus the area of that rectangle, that is base times height, times the distance from the neutral axis to the centroid of that area. So let's say that's y1. So we have y1 squared. Okay, so we have 112. Our base here, that's 100. Our height, that is 20. That's the thickness cube plus the area of the rectangle. We have 100 times 20 times our y1 here. Now we can compute y1 by first computing the distance from the neutral axis to the top surface. We have to compute this distance first, that is 310 minus 127.5, 182.5. Okay, that is the distance from neutral axis to the top surface. We have our y1, that is equal to 182.5 minus the half of the thickness, since this one is 10, correct? Minus 10, then we have 172.5 millimeter. So therefore, we have here 172.5, and that, since that is squared, and this gives us 595,791,66.67. That is in millimeter raised to the 4. Okay, so that is the moment or transfer moment of inertia of our section 1. Now for section 2, we have, let's say that is our transfer moment of inertia of section 2, that is equal to, that is still a rectangle, so we have gross moment of inertia, that is 112 BH cube. So 112, our base here is the thickness, 20. Okay, the thickness times the height. The height is equal to 270 cube plus the area of that rectangle, that is 270 times 20. Okay, and D here, that is the distance from the centroid of this area 2 to the neutral axis. So let's say, or let's assume that we have our distance, this one, Let's say that's our y2. Now our y2 here, that is equal to, now we know that our centroid is, that is 1/2 of 270 of this rectangle, that is 135. Correct? So therefore, we can compute y2, this one. In this expression, we have 182.5. That is the distance from the neutral axis to the top surface, minus the thickness 20, okay, minus 135. So our y2 here is equal to 27.5 millimeter. So therefore, this y2 here, the distance from the neutral axis, is equal to 27.5, and this is the distance from the centroid of area 2 to the neutral axis. So we have here 27.5. Take note, it is being squared. So we have our moment of inertia, or the transfer moment of inertia of section 2, that is 368,887,150. So this is 36,888,750, that is in millimeter to the fourth. Lastly, we have the transfer moment of inertia of our, this one, section 3, that is, let's say that is INA3 equal to 1/12 times the base, that is 210, times the height, that is 20 raised to the 3, okay, that's BH cube over 12, then plus the area, that is 1 or 210 times 20, correct, times the centroid to the neutral axis. So let's say this one, centroid, let's say that's y3, and our y3 there is equal to, we have the distance from the neutral axis to the bottom surface, we have 127.5 minus the half of the thickness, since this one is 10 minus 10, then we have 117.5 millimeter. Okay, that's the center or the centroid of area 3, section 3 to the neutral axis. So we have 117.5 squared. So we have our inertia of our section 3 transferred to our neutral axis. We have 58126.250 millimeter to the fourth. Okay, so we have now our neutral axis for the entire cross section, that is just our moment of inertia in the neutral axis equal to inertia of our 3 plus the inertia of 2 plus the inertia of our section 1, and then you add all these inertias, and the result is 154,594,166.7, and this is in millimeter to the fourth. So we have now our moment of inertia for the entire section that is asymmetrical with respect to the x-axis. Okay, so we can now use this in our formula for flexural stress. We have bending stress is equal to the moment C over I. So our first question here is to determine the maximum tension bending stress at any location along the beam. Okay, so first is the maximum tension bending stress. Now we know that we could have two possible locations of our tension or tensile bending stress. It could be at the top surface or at the bottom surface. Okay, so we do not know yet where is the location of our tension or tensile bending stress. Now we can solve either of using these two stresses here. Now we know that this is positive bending, that is 7.829. Again, when we say positive bending, we have this type of bending wherein at the bottom surface we have tension and at the top surface we have compression. Okay, so we can check, okay, we can use this 7.829 as our moment, and our tension here is at the bottom. So therefore, in that case, our tension occurs at the surface, at the bottom surface of our cross-section. So we have bending stress is equal to the moment. This is 7.829, this one. Now take note that it's in kilonewton meters, so we multiply 10 raised to the 6 so that we could have Newton millimeter. Now, the C here, since we are referring to the tensile point or tensile surface, we know that our tensile surface is at the bottom since we have positive bending, since we are using 7.829 here. So therefore, our C here is from the neutral axis to the bottom surface, and the distance is 127.5 millimeter. So therefore, we have 127.5 millimeter over our moment of inertia for this entire beam, that is 154.594166.7. Again, this is letter A of our question. So we have our flexural stress equal to 6.457, that is in megapascal. So therefore, this is the tensile stress. But we cannot say that this is the maximum tensile stress, since we have another type of moment here that is in negative bending, this one that is in negative 8.175 kilonewton meter. So therefore, we could have another case that is in negative bending. Now, in the case of a rectangular beam, or a rectangular section beam wherein we have symmetrical cross-section with respect to the x-axis and the y-axis, in computing for the maximum tensile and maximum compressive bending stress, you just need to point, or you just need to use the maximum moment along the beam. Since we know that using that maximum moment, we could compute the maximum tensile and compression stress. Now, if we have the same loadings, the same type of beam, but we have a different cross-section, okay, and we have a rectangular cross-section, now in that case, we do not need to have two cases. We just need to get the maximum moment, and maximum moment there is 8.175, and use this 8.175 to compute for both the maximum and tension bending stress. So we do not need to have two cases, just like what I did here. Again, since we have a symmetrical cross-section wherein we have two different value of C from the neutral axis. Okay, just like this one, we have 182.5 and 127.5 from the top and bottom respectively. So therefore, we could have different result of flexural stress from different, or using the different type of moment, or type of bending rather. Okay, so therefore, in this case of 8.17, we have at the top surface, that is, we have tension. At the bottom surface, we have compression. Okay, so therefore, by using the flexural stress, we could have different C value. Okay, so therefore, we have flexural stress is equal to times that is 8.175, okay, times 10 raised to the 6 times the C. Take note the location of our tensile stress at the top surface. So therefore, we have the C distance, that is 182.5 from the neutral axis, since that is on the top surface, over the moment of inertia of the neutral axis, that is 154594166.7, and our flexural stress here, that is equal to 9.651, okay, that is in megapascal. So this is the tensile stress using different moment. Now, since we are looking for the maximum tensile flexural stress, so therefore our answer here is this one. This is the maximum, 9.651 megapascal. So this is our final answer for letter A. See, in letter B, we are asked to determine the maximum compression bending stress at any location along the beam. So we still have two different cases. If we have a positive bending, since this is smiling, this positive bending since this is smiling, and we also have negative bending here. So for positive bending, we will be using 7.829 here. So we have flexural stress equal to the moment 7.829 times 10 raised to the 6 to convert into Newton millimeter times C. Take note, we have positive bending and we are looking for the compressive stress. So therefore, our C here is from the neutral axis to the top surface. Okay? So if this is our neutral axis. And that distance is 182.5. So we have 182.5 over the moment of inertia, that is 154.594166.7. So we have our flexural stress here is equal to 9.242 megapascal. So this is a compressive bending stress. Now for the second case, we have negative bending, this one, wherein our compressive point is on the bottom surface. So we will be using 8.175 as our moment. So we have our moment, that is 8.175 multiplied by 10 raised to the 6 times our C here, that is since we have our compressive bending stress on the bottom, we have to use 127.5 millimeter, that is the distance from the neutral axis, over the moment of inertia. And we have our bending stress 6.742 megapascal, and again this is a compressive bending stress. Since we are asked to compute or to determine the maximum compressive stress along the beam, so therefore we will be using this stress here, that is 9.242 megapascal. Okay, and this is now our maximum compressive bending stress, which is asked in question letter B. Okay, and that ends our example number 2. Okay, so if you have questions, you can comment it down in the comment section below. And for more videos, don't forget to like and subscribe. See you again in the next video. Thank you very much for listening.